The ends Q and R of two thin wires PQ and RS are soldered or joined together. Initially, each of the wires has a length of 1 meter at 10 degrees Celsius. Now the end P is maintained at 10 degrees Celsius while the end S is heated and maintained at 400 degrees Celsius. The system is thermally insulated from its surroundings. If the thermal conductivity of the wire PQ is twice that of wire RS and the coefficient of linear expansion for PQ is 1.2 into 10 raised to negative 5 per Kelvin, the change in the length of the wire PQ is. Okay, we will first draw the figure. Let me show wire PQ in blue color. And let me show the wire RS in blue color. PQ red, RS blue. Okay, both these wires, keep in mind, they both have length 1 meter each before they were heated. Okay. End P is maintained at 10 degrees Celsius. Okay. End S is heated and maintained at 400 degrees Celsius. Okay. The system is thermally insulated from its surroundings. Thermal conductivity of wire PQ. Let us call it kappa. So kappa PQ is twice that of wire RS. So twice kappa RS, comma. Coefficient of linear thermal expansion for PQ, alpha PQ, is equal to 1.2 into 10 raised to negative 5 per Kelvin. And we have to find the change in length of the wire PQ. Fine. So first of all, we will recall the formula that we have to use to calculate the change in length. So this takes us to thermal properties of matter, which says new length L new is equal to L old into bracket 1 plus alpha into delta T. Do you remember this formula from thermal properties of matter? Okay. L plus alpha L delta T. L plus alpha L delta T. Now what do we want? We want change in length. Delta L has to be L nu minus L. So that will be alpha L delta T. Okay. Now see, do we know alpha? Yes. We know alpha. Do we know the original length? Yes, we know. We do. But what we don't know is delta T. And even in delta T, we actually know this 10. So if we find the temperature of the junction, okay, it basically tells us that there is temperature gradient, constant temperature gradient between P and Q, which will lead to continuous heat flow from S to P, because heat always flows from body at a higher temperature to a body at a lower temperature. One more additional thing which I would like you to observe, and that is nowhere here we are considering or paying attention to time. Have you noticed that? When they say maintained at 10 degrees Celsius, 400 degrees Celsius, okay, and initially 10, P is maintained at 10, it means this is going to be which solution? Steady state solution. Because I have told you, steady means things do not change with time. They may change with space, but they never change with time. Do you follow this? Yes. Have you made any attempts in finding the junction temperature? If yes, what attempts? How have you tackled that problem? By the way, all of you, had you reached this stage or no? You had. Okay.
Yes, sir. After the second.
Okay. So the target is clear, right? The target is to determine the temperature of the junction. Once we find it, we have to put it here. Is that clear? Okay. Now think about the same situation. Think about the same situation in terms of electricity. In terms of electricity. Suppose there is a resistance PR and a resistance RS here. Okay. Yeah. And think of this delta V potential difference between S and P as delta T. Because why is current flowing after all? Current is flowing because there is temperature difference or there is potential difference. Okay. So what is current? Current is analogous to rate of heat flow. Do you agree to this? dq by dt, which is steady, or we can call it q dot. We can call it q dot. Is that clear?
Yes, sir.
Okay. What else should we consider? Do we need to consider? Resistance. And here I would like to consider the thermal resistance. Okay, here I would like to consider the thermal resistance. Can I say that Q dot is same? Look, these resistors are connected in series. That means same current must be flowing through them. Got the point? Okay, if same current flows through them, what equation can I write? Okay, what equation can I write? Look, Ohm's law tells me that delta V is equal to IR, but now I know that current is same. Current is same for both, so I can write delta V by R as constant. So in our case, what can I write? I can say delta T by Q dot for PQ must be delta T by Q dot for RS. Have you followed this step?
Yes,
If you haven't, please ask me. Acha. Now, is there any formula that you know which relates the rate of heat flow with the temperature gradient? Fourier's law. Okay, Q dot is negative kappa A dt by dx. Have you seen this law? How? This is heat conduction. Haven't you seen this law? Q dot is negative kappa A dt by dx.
I have, sir.
You have. Okay, well, in case if you did not know that, this is the law called Fourier's law of heat conduction. What is the negative sign doing there? Negative sign basically signifies that heat is going to flow when temperature is in the direction where temperature is decreasing. Okay, that's our standard time. Okay. Now see, what we are going to do is we are going to write dt by dx as delta d by delta L, because we know that Q dot is constant. Now see, this is application of derivative. Because we are saying that Q dot is a constant, did we not state that here? A steady state, Q dot doesn't change with time. Which means dt by dx, which was the only variable, I can treat it as a constant and I can treat it as delta t by delta L. Do you follow this or not? You do. Okay, now go back to the main equation that we have developed. Go back to this equation that we have developed. For PQ, what will be delta T? For PQ, delta T will be T minus 10. For PQ, delta T will be T minus 10. And for RS, delta T will be 400 minus T. 400 minus T junction is T. Okay. Now, let us ignore the negative sign. Okay. Let us ignore the negative sign. Sorry, my bad. I took the incorrect equation. I should have equated dq by dt. Q dot is the current, right? Sorry, my bad. Current is same, right? Current is same. In series, same current. So I should have equated q dot and not delta t by q dot. Sorry. So it's not delta v. Oh, delta v by r is constant. That is right. But I incorrectly said that resistance is q dot. Sorry, my bad. Current is constant. Current is constant. I is same. But what is current? Q dot. So q dot pq is equal to q dot rs. The resistances are not same. The currents are same. The heat flow rates are same. So q dot pq is equal to q dot rs. Now that q dot is here. Negative kappa a dt by dx. Now let us equate them. Okay, let us equate them. Therefore, kappa pq, area pq into T minus 10 upon 1 meter equal to thermal conductivity of Rs, area of Rs into 400 minus T upon 1 meter. Same length. Okay? Now, have they commented anything about the wire diameters? No. They have just said thin wires. So we have to assume that they have same cross-sectional area. So this is going to get cancelled. ARS and APQ. Okay. Now, have they related thermal conductivities? Kappa PQ is 2 kappa RS. Yes?
How is delta L is changing in that?
No. In this case, delta L is the distance that you are using to calculate the temperature gradient. Okay. Yes. So what equation will we get? 2T minus 10 is equal to 400 minus T. Therefore, 2T minus 20 is equal to 400 minus T. Bring T here. 2T plus T, 3T, 420. So how much will be T? 420 by 3. 140 degrees Celsius. Yes, now we got T as 140. We can put it here. (1.2 into 10 raised to negative 5 into 130). Okay. Into 130. So bring the 0 here. Look at the options. Options are in millimeters. Okay, options are in millimeters. So we would like to have this as 10 raised to negative 3. Okay, so how much is this? (1.56 into 10 raised to negative 3). Option C. Got the problem? Okay. Leaving the calculation part, note that this problem actually involves two aspects. The first aspect is to, in this case, we actually started with what we wanted. Okay, we wrote down a formula and it turned out that there was one unknown which we had to determine. Okay, so that was the thermal properties of matter, first part. But even in the second part, we made use of one of the laws in physics called Fourier's law. Okay, which relates the rate of heat flowing through a certain conducting medium having cross-sectional area A, thermal conductivity kappa, and this is dt by dx. This particular law was made use of, and second thing is we use the analogy between potential difference, temperature difference, current, rate of heat flow, and therefore resistance became the ratio of delta V and I. Okay, so we did that. Because these wires were in series, we used the fact that current is same when resistors are in series. So Q dot was considered to be same through RS and through PQ. And that basically got us the other equation that we used to find TQR. And rest is just simple mathematics and we got it. Okay?